Okay, please.
You have the work. Okay. Can I start? Yeah. Okay. So thanks. I want to thank the organizers for having me. This is the first conference after a little bit and the first time in Corfu, so double the pleasure. I will present a little work I did with Jernej and Svetlana in, at the Ješek Stefan, just trying to correlate the G-2 for the lepton and the Higgs decay to a lepton pair in this MEF framework. And I'll start with the spoilers of the finale. What we do is that we show that we just need a small set of operators in the MEF to describe these two observables, that the one loop renormalization group equation correlates the operator describing them, so correlates the observables, and this, in this RG, there are chirally enhanced terms that will enter in the one loop matching conditions. Of course, one then can do the numerical analysis and have hints on the new physics scale. And lastly, I will show that this three-level matching plus the running is actually a very good, can numerically have a very good approximation of full theory calculations. So it can catch the dominant effects of new physics theories. I'll just start with a very quick introduction to MEF. And the idea is that when we have heavy new physics on the left side here, there is no pointer, okay. We have heavy physics on the left side, we know that we can describe at low energies, so when Q squared, with the energies we're looking at is much less than the new physics scale lambda, we can describe this with effective operators, with an effective interaction. We can think of the weak interaction just for a clear picture. And the long distance physics in the EFT is described by the operators that contains the light degrees of freedoms in the theory. And this is a question mark because what is the light with respect to what? While all the new physics, the short distance, is captured by the so-called Wilson coefficients, which depend on the new physics scale, on powers of new physics scale. And if you think about this new theory here as the double boson and this as weak interaction, then the Wilson coefficient catch the Fermi constant, so it's proportional to 1 over the weak scale squared, and the operators are just the usual V minus A, the vector minus axial interaction between fermions. So now we have two ways we can approach, we can use EFT. One is the so-called, I called top-down. We start by defining our favorite new physics model. Then we match it. That is, we ask that the amplitude in the of the new physics model is the same as the one from the EFT, and then we do all the prediction and calculations that we like. Then the other, if we follow the red arrow, we can use the bottom-up approach. That is, we can build a complete basis at the low scale, and here the question mark, low scale, light with respect to what, and then we have to fit all the coefficient with the experiments. So now the problem is, depending on the scale, we have different EFTs. If we start at very high scales above the electroweak, we have the so-called MEF, where all the degrees of freedom in the standard model are light, and the famous Warsaw basis, which contains, I think, more than 2,000 operators, is the one describing the standard model effective theory. If we keep going down, then at some point we get to the weak scale at which, for example, the top quark and the Higgs and the SU2 bosons become heavy, so we have to define an EFT which does not contain this degrees of freedom, so-called high flavor, and then we can keep going down to the bottom mass, the bottom threshold, the charm, and then the nuclear, etc., at which we have the so-called low energy effective theory, in which we only have like fermions, gluons, and photons. What we're interested in, here I'm making just an example, just a schematic example with two operators. For example, when we're in this MEF, then we have to consider the heavy, the SU2 gauge bosons. And then the gauge invariant operators needs, for example, in this case, if we want to couple left-handed with the right-handed, as you can imagine, to generate a G-2, then we need the gauge invariant operators needs to contain a Higgs here. While on the left side, in the low energy case, there is no heavy gauge bosons, there is no Higgs, so we only have fermions and photon, and this operator generates, for example, the G-2. what we're interested in is that if we want to connect different scales, we need to consider the RG running, especially if we want to include one loop quantum corrections. Then we need to consider the RG running. And the two main effects we are interested in is the operator mixing. That is, one operator, one loop can generate another in a very basic way. I'm making, again, just a schematic example. We have the photon vectors with fermions. If we have a 4 fermion operator in this MEFT, then we can close the loop, we can attach a photon, and at one loop we have generated the G-2, and this, and then this will enter the normalization group equations. And then the other effect we're interested in is the threshold matching. That is, once we get to the threshold, we have to match the coefficient in one basis with the coefficients in the other basis. And what can happen, for example, if you think about the top quark, is that the top loop will be present on this side, but will not be present on this other side. So top loop contribution will appear in the matching between the two bases. Luckily, I'm not gonna derive the result. I'm gonna use them. A set of papers that already did the complete one loop RGE in SMEFT. This is the famous trilogy of paper from Jenkins, Manuel, and others. And then there is a recent paper that computed the complete one loop SMEFT matching into the low energy effective theory. So this is already done. Then let's go look at these two observables in particular. So we're looking at the left-hand sector. For the Higgs decay, it's easy. We have in the standard model, we just have the usual Yukawa interaction, where the Yukawa interaction, Yukawa trade couples the left-handed and right-handed leptons with the Higgs, and then the Yukawa coupling is just proportional to the mass. Then we can look at the two bases. On the low energy side, we have we can write the new physics effect as a shift in the Yukawa term. We only have the Higgs and the leptons. While on the SMEFT side, the first gauge invariant term that contributes to the Higgs decay includes, as you can see, 3 Higgs and then the left hand the doublet and the right hand the singlet. So it's generating this sort of diagrams with 3. The matching at 3 level is actually easy to think about. 2 of these get averse, and then we just generated the low energy observable. And how can we put this? The kappa factor is defined as the Higgs width in 2 leptons over the standard model Higgs width, and this is just as proportional to this new low energy coefficient. On the G-2 side, this is from the Peskin Schroeder, you can get that the G-2, or the anomalous magnetic moment, is proportional to the form factor F2 at the zero momentum exchanged. And this is also suggesting that on the low energy side, the operator should look like a tensor interaction between the leptons. So as I said, this is we normalize it with the mass and the electric charge. And at the low energy, we generate the G-2 with this operator. On the SMEFT side, now we have, again, as a low degrees of freedom, we have the SU2 gauge bosons. So we have 2 operators, one with the W, one with the B, but the diagram is, as you can see, it's the same for both of them. And you can imagine, again, the 3-level matching, it's easy. The W and the B have a different combination with the cosine and sine of the weak angle. They mix into the photon. So once we take into account this mixing, then the 3-level matching, it's easy to compute just by hand. And since we use this normalization, then the observable, there is the famous delta A for the lepton, is just proportional to this low energy coefficient. This is all 3-level. Then one easy observation one can do is that, let's say we don't care about Yukawa correction proportional to Yukawa, except of course the top. Now we just need 2 more operators to complete the basis. And this operator suggests the 4th fermion operator. Here on the left, we have a lepton-lepton coupling with quark-quark, and this epsilon is the Levi-Civita tensor with the SU2 indices. We call it O5 and O4, and O5 is exactly the same, but with a tensor. So we have this 2-gauge invariant structure we can build, And this, if one goes and look at the entire one loop RGE, are the only two that give correction proportional to the Tokugawa. There's actually the two I've written by hand. If we now go to the again to the Higgs decay to lepton, then one on the left side we have an additional contribution. You can imagine we close the loop with the top loop. We attach the Higgs and we get a mixing. So C prime dot as a term proportional to Tokugawa to the third. Similar for the G minus 2, we have the 3 level as I said before, and then we have the O5. The O5 now as a top loop. Here it's I didn't write it, but there must be a chirality flip so that we can get a G minus 2 like structure. And this chirality flip reflects in the fact that the normalization equation for the G minus 2 operators is proportional to the Tokugawa. And I'm not writing the one loop matching just because I don't think it's very enlightening to have these huge equations. But there is a paper that solves it, so we just use the result. Once we have this, once we have built the framework, then now we can start see what's the consequence from the phenol point of view. And the guidelines are very easy. We have on the left, we have the two operators I showed before that describe the shift of low energy in the Higgs decay and G minus 2. And on this left side, we only need these 5 operators to describe both the 3 level and the one loop contribution to these 2 observables. So what we do, one can assume an initial condition. Of course, the infinite combination of initial conditions at the high scale. So to make it easy, we just pick 5 different conditions, where is one operator, one coefficient is set to 1 at the high scale and all the others set to 0. And one can leave more complicated combination to some model specific case. Then one can perform the numerical running from the heavy scale to the weak scale, match it to the low energy, including a loop. And then one can compute the effect on the new observables, taking into account the fact that there was correlation between the two. There is one operator could generate the other. And before anyone asks, yes, there is electron weak running from the left to the left case, but since we're looking at lepton in the lepton sector for G minus 2 and Higgs decay, we neglect this running, which is usually proportional to powers of alpha. So we only take into account the running from the heavy scale to the weak scale. Good. So we want to do this exercise for electron and tau. I'll jump to the muon for a simple reason. We want to correlate G minus 2 and Higgs decay, but in the electron case, we have a very precise measurement of G minus 2, but the Higgs decay, we are very far away from any sensitivity. On the tau case, we have the opposite problem. We have a very precise Higgs to tau measurements, but the G minus 2, the anomalous magnetic moment for the tau is actually very hard to measure. So we don't have actually the current bounds from even future colliders are orders of magnitude above the standard model predictions. So I'll jump to the muon case, in which right now it's the sweet spot for this. We have a recent measurement of at CMS, for example, of Higgs to mu, I've been shown before, and we also have some. So here, this plot shows the Higgs coupling with respect to the particle mass, and it beautifully fits for the moment all the second and third generation. And we also have projections on this kappa from future experiments. So the high Lumi, LHC, and the FCC, which is going to improve orders of magnitude this sensitivity. While on the other side, we have the famous G minus 2 of the muon, discrepancy. If you, I'm going to be agnostic, but if you believe the theory initiative, or okay, I'm not going to say more of this, but if you look at the theory initiative prediction, you have a 4 sigma discrepancy with the experimental average of the Fermilab and Brookhaven experiment. If you look at the BMW lattice calculations, we only have a 1.5 sigma, but there is still some discrepancy. So I'll just consider both of them. And what you can do is that then what I described before, there is taking the for each scale, you take one initial condition, you do the running, the numerical running, and then you look how this, you compute the observable, and you look how this compare with the experimental bounds. And how to read this plot is that, for example, if we pick the scale of 10 to the 4, which is 1 TeV, then let's start here. For the G-2, you can see that the C4, the red, the color are not very clear, but this is red. And C4 is the scalar operator, the one coupling leptons and quark in a scalar fashion. This would this would actually be favored by G-2. The upper band here is Fermilab, and the purple band is the BMW lattice. This would be favored at the scale already of the below the TeV, below the tens of TeV, here. And if you look at the same scale on the Higgs to lepton side, then this scale can actually be probed by already the high-Lumi upgrade of the LHC. On the other hand, if you look at different models, for example, models that generate tensor coupling with that generate at the heavy scale only tensor coupling with the leptons and quarks, then yes, for example, you can probe it already at FCC or a high Lumi at the tens of TeV scale, but then it would generate a ginormous contribution to G-2. So the accessible scales for this model have to be, well, looking at the Fermilab, they have to be below, have to be above the 10 to the 5 scale. So playing this game, one can have an idea where the new physics scale for this model are, and in particular is suggesting that if we have a heavy scalar model, or a model that includes some heavy scalar that generates this C4, then one can already solve the G-2 discrepancy and probe this model at the near future collider experiment already at this not so heavy scale, say less than 10 TeV. So this was for the Kino part. Then one can, or as I said before, the bottom-up approach. Now one can look at the other side and see how well my SMEFT, my EFT can reproduce full theory results, or how effective is this effective theory, and how long do I have? Should I go into?
You have 11 minutes.
11 minutes. Okay. So. Okay. Maybe I'll finish it. It's okay. I think the idea here is that I don't like to go too much into model building and specific of the models. The idea here is the same for the two cases, the 2 Higgs submodel and scalar leptoquarks. We have some heavy scalar, and this heavy scalar, which in one case is the second is 2 Higgs, and in the second case is just a scalar leptoquark. This heavy scalar couples with the quarks and couples also with the leptons, and thus will generate will match with the scalar operators in the EFT. I think the nice is okay. That's the idea for both models. Now for the 2 Higgs submodel, okay, one can start building very easy model instead of going into models with many parameters. One can just look at the decoupling limit, in which all these all these rotations in which one mixes the 2 scalars, the 2 doublets, are 0. And so what we want to end up is just a model that has heavy scalars. That I'm saying this a lot. And what we can assume is that these heavy scalars in the 2 Higgs double model we generate, we have 3 heavy scalars. One is a charged heavy Higgs, one is a neutral pseudoscalar, and one is a neutral scalar. And in this limit, one can have in which we have no mixing and no rotation angle. One can have that these 3 have the same mass, apart from a factor of 1 over square root of 2. And then to make the model even easier, we just assume that we have only diagonal coupling, so we're not looking at any flavor violation. And this heavy Higgs coupled to the up quarks and the leptons. So this long Lagrangian is just to say that this phi2, which is the heavy Higgs, couples to the leptons and couples to the up quarks. What happens there is that the three-level matching with this MEFT is very easy. It's just that the one generates the C4, if you remember, is the scalar operator, and the matching is just proportional to the two couplings. Y prime is the coupling to the top, Y prime L is the coupling to the leptons over the mass squared of the heavy Higgs. And then, so what we want to do is when we want to compare the full theory calculations, in which in this case is actually not dominated by the one loop for the G-2, but it's actually dominated by the two loop RZ diagrams of this sort. And that's because the one loop are chirally suppressed. One needs to have a chirality flip in the one loop and one loop diagram to one needs to generate the G-2. And this two loop already is dominated by these leading modules of the top quark. We are assuming there is a top quark in the loop, or the heavy mass. So this is already suggesting that these two loops will be the one with the leading logs. What we do is that then we can compute the same process in the way I described before. There is matching with the three-level, matching with the this MEFT, and then running. And actually, the nice part of this plot is that you cannot see all three lines because they overlap very nicely. What are these three lines? The red one here is the calculation using this MEFT. There is matching at three level using that initial condition, doing the running, and then the matching with the low energy, and then the computing the observables. And then the blue line is the complete model calculations. So what we're seeing here is that for heavy scales, this MEFT running is able to catch the leading log behavior and is able to reproduce the same result of the full theory. This is in two cases. In two cases, one is just fixing the coupling and changing the mass, and the other one is fixing the heavy mass to 10 to the 4 GeV, and then changing the couplings around one. So what we're seeing is that this MEFT is able to reproduce this one. This is for the two Higgs, for the G-2, and instead for the Higgs decay, we have a similar one loop diagram, which is not chirally suppressed, and we get exactly the same result. So the two Higgs double model, which is the blue line, perfectly, I don't want to say perfectly because it's a log plot, but we checked there is around 95% agreement, matched with this MEFT calculations. Same thing with the scalar octoquarks. Again, it's not very useful to go into the complete model building. Just the idea is that we have 12 different realization of scalar octoquark depending on the gauge number we want to give. We just focus on these two, S1 and R2, which couples, S1 couples left-handed quarks with left-handed leptons, and right-handed up quarks with right-handed leptons. R2 instead couples right-handed leptons with right-handed quarks with left-handed leptons, and so on. And you can see that these two, then by fixing the interaction terms, one can generate the scalar operators with quarks and leptons and the tensor one. And the matching, there are a lot of indices, but actually when we look at just the flavor conserving terms, it's much easier. What we have is that both of them are generated. So this is one case in which we have a different combination of a more complicated initial condition when we generate both observables, both operators in the S1 and R2 case. And as I said, the three-level matching to MEFT, then it's really easy. Both of them are generated with the same coefficient, just with a proportionality term. For the S1 is a minus and R2 is a plus. And this matching just depends on the coupling again over the mass of the left quark. Easy. Then, okay, I'm almost done. Then one can do the same game as before. We go in the literature and we take the one loop calculated amplitudes for the G-2 and the Higgs decay, and then who's in front of the, and then we can do the same game. That is, we can compare the one loop calculations for the leptoquarks with the MEFT one. That is again matching a 3 level, doing the running, and then calculating the observables. And again, I'm not commenting on the validity of this model because, okay, just that for the leptoquark, since we have both operators, the scale at which it can solve the G-2, it's much higher. But again, the interesting result is that, again, we have a nice matching between the two calculations. So what I'm meaning is that we just use 2 examples. I want to stress the fact that these examples are not they don't have some peculiar, we didn't pick this for some specific reason. It's just heavy models with heavy scalars that generates G-2 and Higgs decay at one loop. And what we get is that depending on the model, this calculation that is matching a 3 level with this MEFT and then doing the running is able to reproduce the numerical result of the full theory calculation. So now the spoilers are becoming the summary. What we did is to show that we need a small set of operators in this MEFT to describe the observables. And in this case, we are limiting ourselves to real non-flavor violating coefficient because we wanted to look at G-2 of the leptons and the Higgs decay, but in general, one can look at different scenarios. For example, CP violating operators. These operators are correlated via one loop RG, and one has to take into account all the terms because the relevant terms which are currently enhanced by the top loop. One can do numerical analysis and get hints of where the new physics scale is for and especially one has to take into account both observables when putting limits on the new physics scale. And lastly, one can do the 3-level matching and then the running, and this can already capture the dominant effects of new physics without needing to do any particular loop calculation with the full theory. And that's all I had.
Oh, that's great. So are there any questions on this talk? Yes. Thank you.
Yes, I don't have control of the slides anymore. Okay, thanks. This one.
Can you take the microphone? Well, no, let me keep this one. It's so confusing.
Sorry?
Are they loop generated in an underlying theory?
Yes. Yes, I mean, one can take into account the complete. Sorry. What I'm saying is that if you want to start, I mean, you have to start with some initial condition, right?
Yeah, but you see, those operators that are loop generated, our coefficients are naturally suppressed for pi at least, right? So, and there are 3-level generators generated, and they don't have a suppression. So I'm just saying that.
Yes. So I think. Yes, I think what we try to do is just at this point is just to be in the effective theory style completely agnostic. We don't know the underlying theory. So what we do, for example, that's what this plot shows is that if you start, for example, with the 4th fermion, which you start it's generated at 3 level, then you have you don't need very high scales to generate the discrepancy, for example, in G-2. You can already do this with a few TV scale. Well, for example, if you see here the green line, which is C1, it doesn't appear because if you start with the C1 operator, so if the underlying theory generates C1 at 3 or loop level, then you have no G-2 effect. That's because there is no mixing. If you look at the complete, I actually have them in the last slide, but it's not very enlightening. Yeah, backup slide with all the equations here. And if you look at the C1 equation, if you look at the C2 and C3 equation that generates G-2, there is no C1 there. So maybe that, I don't know if that's what you were asking.
I actually have one question. Obviously, it's crucial whether or not this BMW lattice calculation, where it looks at B is Budapest, W is Wuppertal, and M is either Mainz or Marseille. So it's Marseille, Budapest, Marseille,
Okay.
and Wuppertal. So 4 months ago, that appeared.
Mm-hmm.
And I guess my question is, in the lattice QCD community, is that generally accepted as being correct, or is it not?
Not part of the lattice QCD
No, I mean,
community.
it's rather crucial whether that, if that's correct. Then
Well, I think
Normally
that's
goes
what
away.
from what I know is that it's peculiar that it's the first result with a very small, in that region that has a very small error bar, which is why there is I think I don't know much, but I think it's the first result in this region that has very small error bars and it's very close to the experimental average.
yeah,
That's why there is some suspicion, but if I have to, I think that there is, I have no idea.
the suspicion. The suspicion is negative or positive?
The suspicion, I would say, is negative because there is, I mean, I think it's interesting in both ways. If it's confirmed, sorry, if it's not confirmed, then there is a discrepancy for sigma in the G-2. If it's confirmed, it means that this white paper and all the data-driven extraction of the form factor has some fundamental problem.
Yeah, does anybody know? Does anybody work on lattice QCD? Or Matthias might know
Probably Professor.
whether it's
more than me.
They only without the microphone. I think the question is only about the error.
Yes.
Calculation is a good calculation. So I don't think that the mind calculation also on top of it. There's a much larger error. The discussion in the electrical is about
This was the first one with a very small error.
of course, there's all the data relations.
Exactly.
I see. There is a Mainz byline on the paper. Somebody from Mainz is on the paper, but also from Marseille. Anyway, well, let's thank the speaker, and then we go on.
Hello.
The next speaker is Jackie Kumar,
Okay.
and the title is Renormalization Group Improved Implications of Semi-Leptonic Operators in Standard Model Effective Field Theory.
Hi, can you hear me?
Yes.
Okay. I will share my slides. Can you see my slides?
Yes, that's perfect. Go ahead.
Okay, thank you very much. So first, let me start by thanking the organizers for this invitation, and apologies that I could not be present in person. So I would be talking about very similar things as in the previous talk. So basically, I will be talking about the semi-leptonic operators and their low energy implications at electroweak scale and at a very low scale like B mass, B meson mass, or tau mass. And I will emphasize, like in the previous talk, the importance of RG renormalization, group running, and operator mixing in this business. So let us start with very basic introductions to the EFTs. It is very nicely sketched out in the previous talk, but let us go over it very fast. So we have different scales in the nature. So as long as we have a scale gap, we can construct EFTs, and this allows us to make the predictions. For instance, this Fermi theory in 1933, without knowing the W boson, so one could write these contact interactions and study the beta decay. So similarly, now at the LSC, as we haven't seen any new physics particles, so this indicates that there might be another scale gap between the electroweak scale and the new physics scale. So this allows us to construct so-called standard model effective field theory. In SMEFT, the field content is the same as of standard model, and electroweak symmetry is broken by still one Higgs doublet as in standard model, and all the higher dimensional operators in SMEFT respect the gauge symmetry of standard model. So for the first time, it was nicely sketched out by Buchmuller and Euler in 1986, all the operators up to dimension 6. Then by Gradziewski et al. Found some operators are redundant, and now the basis, final basis is known by the name of Warsaw basis, which has 59 baryon number conserving operators. So when we do a phenomenological analysis using SMEFT, so this is a general strategy that we follow. We have a new physics model at high scale at lambda, and on integrating out the new physics particles, we get a tower of higher dimensional operators, SMEFT operators. Then in order to calculate observables at the low energy, for example, at the electric scale, one has to run down to the electric scale using the SMEFT RGEs. And if you want to calculate even lower energy observables, then at the electric weak scale, we need to switch to another effective theories called weak effective theory, or also known as low energy effective theories left. And then further one has to run down to very low scales, and there you can use these Wilson coefficients to calculate various low energy observables. So in the present talk, we will be focusing mainly on the semi-leptonic operators. Semi-leptonic operators, in generally, you can write them as L bar L, Q bar Q. Here, X defines the Lorentz structure or SU2 structure. So in this talk, I will be focusing on mainly on the vector operators, in which the Dirac structure is like gamma mu, gamma mu. In the previous slide, as you saw some examples with the even scalar and tensor operators, semi-leptonic operators. Okay, so L here can be a doublet or a singlet, right-handed, which defines the right-handed leptons. Similarly, Q can be a doublet or a singlet quarks. So excluding the flavor structure, in SMEFT, we have total 7 vector semi-leptonic operators. So one thing, we will assume that there is no quark flavor violation at the new physics scale. As you know, if you allow quark flavor violation, then these semi-leptonic operators enter into this flavor violating B decays, K decays, which is very extensively studied in the literature. So we will not repeat that here, and rather focus on the operators which conserve the quark flavor at the high scale, but these may violate the lepton flavor, for example. So on this basis, we can divide the operators into 2 categories. Delta F equal to 0, 0. That means there is no lepton flavor violation, as well as there is no quark flavor violation. So with that, you can have these 6 possible flavor structures. Then you can have operators which violate the lepton flavor, but conserve the quark flavor. So then you can have 9 possible flavor structures. So these are the 7 operators, vector operators in SMEFT with different chiralities. With left, you can have 2 operators, then with left, right, and right, right. So total we have 7 operators, 7 semi-leptonic operators, which we want to focus on in this talk. Okay, so the effective Hamiltonian, you can write it, or Lagrangian, you can write it like CIOI, but CIs here are the Wilson coefficients, which are the scale dependent quantities. Actually, what happens is that At one loop level, for example, when you calculate these loops, they diverge, and you have to renormalize and add the counter terms to normalize the theory. And these counter terms, to kill the poles, so they contribute to the anomalous dimension of these operators. So you can describe the RGEs using this equation, where C dot is equal to 16 pi square mu dc over d mu is equal to gamma times C. So this is a matrix equation where C is a vector of various Wilson coefficients, and gamma is an anomalous dimensional matrix. And in SMEFT, this matrix is known for the full Warsaw basis at one loop order, including the gauge dependence, eco dependence is calculated by these people. Okay, so now what we do, we go to this full anomalous dimension matrix calculated by Alonso, Manohar, and collaborators, and identify all possible terms which could be important for the semi-electronic operators of our interest. So doing so, we find that the semi-electronic operators can mix with these two categories of operators. So one is psi square, phi square d type operators, so which are made up of two Higgs fields like phi dagger phi, and there is then one fermion current psi bar psi. So it could be L bar L, Q bar Q. So there are various possibilities which give rise to these different sorts of operators. And then we have purely leptonic operators like L bar L, L bar L. So there are three of them. So to understand that, you can imagine this kind of penguin, but of course there could be other diagrams apart from this. So you can, for example, if you insert a semi-leptonic operator here, and imagine these two upper legs are leptons, and if you close this quark loop, you can close the quark loop because we have assumed that the flavor is conserved, quark flavor is conserved at the high scale. So all the operators have like Q1, Q1 or Q2, Q2. There's no flavor violation. So you can close this loop, and then here you can attach the leptons. So in this way, you generate purely leptonic operators from semi-leptonic operators. So, okay, so let us look at the operator mixing structure a little bit more closely. So first we consider the operators which conserve lepton flavor as well as quark flavor. So that's why the indices are here II, KK. So I and K can be different, but they conserve the flavor. On the left-hand side, you can see these operators can mix with the psi square, phi square, D type operators, which are also flavor conserving. So, and this happens through the gauge couplings, loops involving the gauge couplings. Here L is defined by this. Okay, apart from this, these flavor conserving semi-leptonic operators, there's another important term in the mixing. So you know that muon decay in standard model is described by this kind of diagram, which is mediated by W. And on integrating out W, you get this kind of effective operator. And in SMEFT, you can have a direct contact interaction for fermion operator, which can also contribute to the muon decay. So it turns out that LQ3 operator, which is shown here on the top, if it is flavor conserving in leptons and quarks, it can mix with this LL1221 operator, and it is described by this equation. So you can see that LQ3 operator can give rise to this 1221 operator. So that means if LQ3 operator is present at the high scale, then through mixing it can affect the muon decay, and hence it can affect the extraction of Fermi constant from muon decay. Okay, so now let us move to semi-leptonic operators which violate the lepton flavor. Okay, again they conserve the quark flavor. So now the indices are IJ, KK. So they can mix with purely leptonic operators, and again psi square, phi square, D type operators. And this time, as you can see, these operators are flavor violating. So for leptonic operators which violate the flavor, and these Higgs operators which also violate the flavor. Again, this happens through the gauge coupling independence. In addition to that, there are also terms in the anomalous dimensional matrix which depend on the Yukawas. So we isolate those terms. So in this case, we keep only the terms which are enhanced by the top Yukawa. So that means the quark flavor is always 3-3 on the right hand side in the semi-electronic operators. And these so through top Yukawa, it can mix with the same operators as in the previous case. This mixing is also present in the gauge couplings and also due to top Yukawa. But of course, this will be more enhanced because of largeness of the top Yukawa. Okay, so that means if you introduce some new interactions at the high scale, you start with some Wilson coefficients, and when you run them down and calculate the observables at the low energy, so at the low energy, the picture can totally change because of this operator mixing. So new operators might appear, some operator which you started with maybe enhanced or suppressed. So it is very important to include the RG facts to correctly predict the low energy implications of new physics, any new physics that you introduce at the high scale. So in this case, we introduce semi-electronic operators. Okay, so now let us look at to what observables these operators can contribute. So that means semi-electronic operators can also contribute to these observables through operator mixing. So as far as chi-square, phi-square, D-type operators are concerned, so these operators, after electroweak symmetry breaking, they can affect the WZ vertices, because when you put the value of phi equal to V 0 V plus H, then you will get the terms yeah. So from the covariant derivative, you will get the gauge fields, and phi dagger phi will become V square, and this will give corrections to the W and Z vertices. And as I explained, this special operator 1 to 2 1, it can contribute to the Fermi constant. So that means semi-electronic operators which conserve the quark flavor as they mix with these operators, they can contribute to, for example, electroweak precision observables. What else these operators can contribute? So if we could keep the this effective vertex from SMAPT, this is LLZ. As I explained, the this chi-square, phi-square, D-type operators after electroweak symmetry breaking, they can contribute to the Z couplings. So if they are flavor violating, so they generate flavor violating Z couplings. And on the right hand side, if you attach another standard model vertex, so combining these two can give rise to lepton flavor violating decays like tau to 3e or tau to mu to 3e. Apart from that, there are also 4 fermion direct contributions to this case. As you saw, these purely leptonic operators are also generated using semi-electronic operators through operator mixing. So both contributions are present, in fact, when you see. Okay, in addition to that, so instead of this leptonic vertex, if this is a quark vertex Z to QQ bar, then it can contribute to hadronic tau decays, for example. But here, note that the semi-electronic operators can itself contribute to the these decays even at tree level. But the flavor has to be 1-1 or 2-2 because these mesons always involve UU bar, DD bar, or SS bar. So at tree level, if you have this flavor structure is 1-1 or 2-2 in the quark sector, then they can contribute also at tree level. But if it's 3-3, then it's only possible through one loop through the operator mixing.
Can you end in minutes, please?
6 minutes.
10.
Okay. So this is a short summary. So as we saw, this psi square, phi square d operators can contribute to WZ couplings, and then these semi-electronic operators can also contribute at tree level to LFE hadronic decays, but with a specific flavor. And at one loop, they can always contribute to LFE decays, which is highlighted in this red box. Okay, so I think the time is not much left, so I will go over it very quickly. So in standard model, charge currents are mediated by W, which are described by this operator. In SMEFT, the charge currents to this operator LQ3 contributes at tree level. So interestingly, what happens is that LQ1 operator mixes with LQ3. So that means LQ1 can also contribute to the charge current decays at one loop level. And these are some examples. So you can, for example, LQ1 1122, it can contribute to K2 L nu bar. Similarly, these are other examples, but the mechanism is same. LQ1 mixes with LQ3. LQ3 gives tree level contribution to the charge decays, and hence this LQ1 gives one loop contribution to the charge decays. Okay, so now this is summary of observables. So we have these 7 operators, 7 semi-electronic operators. If they are quark flavor conserving, they enter in electroweak precision observables. If they violate the lepton flavor and conserve the quark flavor, they can contribute to LFP purely leptonic decays or hadronic decays, LFP hadronic decays. And also this this operator can mix with LQ3 and contribute to the charge current decays. So let us look at some correlations. As you see, some of the operators are common in different observables. For example, 111 contribute to electroweak precision decays. It also contributes to charge current decays. Okay, so that means this can introduce interesting correlations. So here we look at the correlation between LQ111 and 1122. So this operator can contribute to electroweak precision decays, for example, through mixing with these operators, psi square, phi square d operators. And LQ1, as I said, it can contribute to LQ3 through operator mixing, and hence it can contribute to the beta decay. See, this is a singlet operator, I mean neutral current, as you look at the high scale, but through mixing it can give rise to the charge currents. And then similarly, through same mechanism with different flavors, LQ1 can contribute to the K decays. And this I haven't explained you very much. So actually LQ1 with the flavor conserving operator can also contribute to flavor violating LQ3 operator through operator mixing. So this happens to the Yukawas, but I haven't explained you this mechanism here. You can find in the paper. So you see that it's very important to take into account all these constraints to have a global picture of the constraints. Similarly, we look at correlations between LQ111 and LQ1122. So LQ3 it gives tree level contribution to the beta decay, but LQ1 contributes at one loop. So that's why if you put them together in the plane, if you apply beta decay and pi to inu constraint, so this is correlated. But you see the constraint on the LQ3 is much stronger as compared to LQ1, of course, because this contributes at tree level and this contributes through operator mixing at one loop. So that's why this is roughly, I think, 1 to 2 order weaker, this constraint on the LQ1. But it's interesting that it can contribute. So it all depends on your new physics model, what kind of size you generate in your model. So similarly, you can have correlations between LQ3. So here we consider lepton flavor violating operators 1311 and 1322. So again, through operator mixing, these can contribute to purely leptonic decays and also hadronic decays of taus. And yeah, here one thing is interesting is that this LQ1 operator it looks like it can contribute to tree level to, for example, tau 2 pi e, tau 2 pi e. But what happens is that in the amplitude, this UU bar and DD bar enter with opposite sign, these Wilson coefficients. And due to SU2 symmetry, the tree level contribution is 0. So that's why it contributes only at one loop. And that's why you see this operator for sure contributes at one loop, LU, and LQ1 could potentially contribute at tree level, but it doesn't. So that's why both of them contributed one loop, and you see the order of constraints. That's why are similar, of the similar order. Okay, similar. You can have more constraints. So because time is up, I will directly go to the conclusions. So the RG running effects are very important to correctly predict the low energy implications of heavy new physics that you introduced at a high scale. And we have demonstrated that semi-electronic operators, quark flavor conserving operators, can enter through operator mixing into various observables like electroweak precision, lepton flavor violating decays, purely leptonic decays, and lepton flavor violating hadronic decays, charge currents, even B decays, flavor violating B decays through Yukawas. And this leads to very interesting correlations between the observables from very, very different sectors. That's all. Thank you very much.
Thank you. Thank you for the nice talk. And are there any questions? The audience? I can't see any questions. So, are there any questions online? No? Okay, well, let's thank the speaker again. And the third speaker is Fiona Kirk.
Thank you.
And the title is Global Analysis of Leptophilic Z prime bosons. Please, is Fiona here or online? Can we contact Fiona Kirk? Oh, you want to switch to the fourth speaker? Are you ready, Albert? Where is he? Yes, you may be called upon. Well, I don't know what's happening with Fiona Kirk. I think, yes, don't go very far. You might get more time, perhaps. Yes. Okay, and then we'll have Daruk. I think we have to go with. So we will temporarily or permanently omit the next speaker, or we'll see what happens. So we'll jump to Professor Albert de Rook, and he will give us a survey of neutrino experiments at CERN. Please. Fiona Kirk is not anywhere to be seen. She's not here and she's not online. I'm just asking to see whether we can give Albert skip for today. Okay, so well, I think Albert has just got another 15 minutes of time.
Very good.
Okay, please go ahead. Yes, I arranged it.
You arranged that, so I got 1 hour now, and
Well, let's go over.
and so then I will really do my best to find these bileptons for you. I mean,
I thought that was
no.
not an hour. You actually
Yeah, don't worry.
you have 45 minutes. How about that?
That's fine. That's fine.
One minute.
Okay, so hi again, and this time the technology is tuned. I hope, you know, good test case, so they could change totally everything. So now everything works. That's good. And then I can even show my own slides. That's very good. So I will be talking about neutrinos and neutrino experiments. In fact, this talk should have been on Friday in the neutrino section. And I could do it on Friday, but from Geneva, and they said, no, you better do it while you're here. That's why I'm here. So it's a bit odd in the rest of the program we had this afternoon, but that's how it came about. I'm not going to talk about neutrino experiments at CERN. That would be a very short talk, because at the moment we don't actually have neutrino experiments at CERN. But CERN is participating in neutrino experiments, which are not their property, but part of the. Well, I think the last experiments at CERN were in fact around the year 2000. As you will see, because there was the OPERA experiment, but even that was not an experiment at CERN. That was an experiment in the Gran Sasso laboratory, for which CERN just delivered the neutrinos. Okay, now more about the history as we come through. Let's talk about things. So it gives me the chance to be not too hastily on the introduction to neutrinos. Many of the things you may know, but some facts may still surprise you from time to time. We know neutrinos have mass. They oscillate, and we come back to that, and also to the dynamics of that, and the experiments, where they are now, where they are going, the future of particularly oscillation experiments, in which CERN happens to be strongly involved now. And but I'll also go on what is new about the neutrino properties, like the mass and the Majorana-Dirac nature of neutrino. I was thinking I would have to skip cosmic neutrinos, maybe not, so given the bit of more relaxed time, and the stellar neutrino searches, which I would have left to Alexei Smirnov for Friday on the theory side, but probably I give something on the data side here as well. And then the novelty, what happens is now that actually in future, and the future starts next year, we will have neutrino experiments at CERN. We are actually going to measure neutrinos again at CERN, not with the specific neutrino beam, but with the LHC, who produce a lot of neutrinos. And there are 2 experiments, in one of them I'm also involved, that are going to do that. Since I didn't know how technology would work, I just put here a picture of me. Maybe I wouldn't be in room, I had no idea. Okay, so neutrinos are still mysterious particles, as we know, just to warm up this slide. They have only left-handed, weak interactions. They were massless for a long time, until 1998. So they discovered they had mass. They are actually the only neutral fermions we have in the standard model. And they could be Majorana or Dirac, meaning they could be their own antiparticle, or the antiparticle could be different from the particle. We actually don't know that yet. Neutrinos are produced everywhere in the sun. atmosphere due to cascades of interactions of cosmic rays with the atmosphere. In supernova explosions, lots of them. In the primordial neutrinos from the Big Bang that were created, they are still around us. There is some, like CMB, there's also a neutrino background still around from that time. Nuclear reactors, of course, create lots of neutrinos. Accelerators can produce neutrinos. And there are also neutrinos while you sit here around you, Churchill neutrinos, radioactive decays. And you may not know that, but you yourself, you emit 4,000 neutrinos per second from your body. That's just potassium decay in you that goes in a beta decay, and yeah, they look like a lot, but you're a bit of a neutrino generator, everybody here. Okay, so to give an idea, in every cube centimeter in this room or elsewhere in the universe, there are on average 300 neutrinos in every cube centimeter. Most of them are coming from the Big Bang. And in fact, since you now know that neutrinos have mass, you have to come to realize that neutrinos can have a speed which is non-relativistic. They can be slow. In fact, 2 out of these 300 typically have a speed which is much less than the speed of light due to their mass and their very low energies. Supernovae give us 10 to the 58 neutrinos in one blast going everywhere. The sun sends us 10 to the 38 neutrinos per second. And for example, the diabases are gigawatt reactors in China, where the diabase experiment is, they give us like 10 times the 21 neutrinos per second. We know neutrinos don't interact much because they are very weak decays, and in fact, the interaction rate goes with the energy of the neutrinos. The lower the energy, less interaction. So one could say that neutrinos are a bit like diamonds forever, except for the very highest neutrinos, the highest energy neutrinos, they do interact and they do disappear in a visible way. But since we create the whole time neutrinos, in fact, the universe constantly actually is like entropy, is like growing neutrino rate which we have around us. So these are the different classes of neutrinos, different used for experiments, like the solar neutrinos, the neutrinos coming from the Big Bang. This is the energy scale of the neutrinos. This is 10 to the minus 6 electron volt here. This is in the MeV range. We have from cosmic rays, backgrounds from all supernovae, atmospheric neutrinos, and coming from cataclysmic events in the cosmos, like active nuclear, active generating nucleus here. From these, particularly the cosmological ones, these ones, and the diffuse background of neutrinos which is around us, which is actually sitting here, but under a large background of other sorts of neutrinos, they have not been observed yet. So if you're young, you want to do an experiment, and like Paul, you want to have a Nobel Prize, this is something you should try to measure, and from the experimental side. Sorry for the joke, Paul. This is the spectrum of the interaction. So the cross section as it grows from, and you see immediately the problem for the Big Bang neutrinos, they have an extremely low cross section, and you have to be very clever to actually going to fish them out. It would be interesting to see these, because with these you would actually study the Big Bang in the first fraction of a second. Not like with the CMB, which is like, the light you see after 200,000 years the universe existed, because before it couldn't go through the universe. Neutrinos don't care about that. They go through things. You will see them actually as they are, being strongly cooled off, of course, due to time and expansion of the universe. So, and then everybody is around. We're sitting mostly here with the measurements: accelerator, atmospheric, supernova. If we are lucky, we were lucky once, we will hope to have it again, solar neutrinos, and so forth, reactor neutrinos. All right, so what are the open questions? Mass values. We know the neutrinos have mass, because they oscillate. But the oscillations tell us only mass differences and in an absolute way. So without any sign on it, we don't know who is the heavier, who is the lighter one, for example. We don't know the absolute values of the mass. Is it electron volts? Not, it's clear, I will show you. Is it milli-electron volt or something? Where are they? There are some constraints given by what we measure in the oscillations. We also don't know if all three neutrinos which we have actually have a mass. The only thing we can say from the oscillation physics is from the three, at least two need to have a mass. Masks, you know, this is such a common word that they may have masks, but they certainly have mass, two of them. And the third one could have mass, but we are not sure about that. The theory would work now also well if the lightest one would be mass zero, for example. The hierarchy we don't know. You will see we'll talk about mass states in a moment, as opposed to flavor states. And they will be given the very exciting names, nu1, nu2, nu3, by lack of imagination. But we don't know which one of these will be the heaviest and which one is the lowest mass state, because we measure only absolute differences and not absolute values of the masses. A very interesting aspect for the neutrinos, which we are hunting with the experiments now, is neutrinos could give us an answer why we are here in this room, in the sense that why there is more matter in the universe than antimatter, and not everything annihilated from the beginning. Then, here. And that comes through a thing that I will show later. If neutrinos are their own antiparticles, we have lepton number violating processes immediately falling out of that. Do right-handed neutrinos exist? We haven't seen them yet. That's different to say that they don't exist. We haven't seen them. They could be because they are much weaker interacting even than the neutrinos we have now, because they don't interact even weakly, but they could only be seen through mixing by the neutrinos which we know, the three neutrinos we are familiar with. Neutrinos also could play a role in dark matter. They could deliver tests of CPT. And obviously in the interactions which we are, one of the things is to watch out for non-standard neutrino interactions outside of the standard model. But we do know neutrinos are chameleons. They can change flavor like chameleons do. So the sun, for example, is one of the sources of neutrinos which has been used. In fact, very early on, you probably remember the solar neutrino problem, Ray Davies experiment, and so forth, Vitals calculations, the whole discussions for 20, 30 years. But finally, both calculations and the measurements seem to be correct, as tedious as they were. I will not go into that. And we understand what happens with neutrinos when produced and on their way coming to us. But now we can use that actually to learn about processes in the sun. What are the generating fusion processes which are there? And there are sun models based on that. And then from these models, if we get it right, we can calculate, for example, the temperature in the sun. So we can learn what is happening in the sun, because these are the messengers that come out immediately of the sun. Light takes about 100,000 years when it's created in the center of the sun before it reaches the surface. Neutrinos, do it in a minute or so or less. And one of the things in there on new data, I should say, is this Borexino measurement, which came in Nature sort of middle this last year, which was actually the first establishing directly that this so-called CNO cycle, long time ago proposed by Weisskopf and collaborators, existed and has now been measured. This is the full spectrum, what they measure from the sun. This is the CNO part. And in this region, the CNO part is the dominant of all these processes, and that led them to make the claim that they have seen this part and could check it. But for oscillations, this is the name of the game. we actually have oscillations of, I give it somewhere, no, I don't have it lately. What you have is, that's one slide missing, I'm sorry, that you have flavor states that mix into flavor eigenstates, I should say, that mix into mass eigenstates, which you have there. And in between is a matrix, a 3x3 matrix, which can be conveniently decomposed in 3 components, which each have one particular rotation matrix, a rotation angle in this matrix. It's either the 2-3 which has the relevant mass components here, the 1-3 and the 1-2 rotation angles in there. And these symbols you see, these are cosines or sines of this angle, like in a normal rotation matrix. So that is what the measurements are after. This is called the Ponte-Corvo-Martin-Nakahava-Sakata matrix, which relates the flavor eigenstates to the mass eigenstates. For charged leptons, the flavor eigenstates and the mass eigenstates coincide. For the neutrinos, the base is rotated between the flavor states and the mass states, and therefore we have this thing at work here. Now, as you see in this game, there are 6 parameters you determine, 3 angles, each one with each of these submatrices. I mean, the whole thing is a product of together. 2 mass differences are going to play a role, and there will be a big mass difference measured and a small mass difference measured. And there is one very interesting part, and this leads to why matter and antimatter could be, ending up differently, particularly at the start of the universe. There's a CP violating phase in this matrix, as you have, for example, in the quark sector, that can give you CP violation. Now, for that, it's important that you see this phase sits here, that the S13, so the sine of the 1-3 angle, must be not 0. If that is 0, we are insensitive in the oscillations to the CP violating phase. And for this to act, then we would not be able to measure it through oscillation experiments. And for this to play a role in the early universe to create the asymmetry we have, this space be to be substantial. We have CP violation in the quark sector as well, but that's many orders of magnitude too small to actually to do the job. So one of the hopes is that actually here it's larger, and the first indications are that it could well be large, although it's still, not a solid on solid grounds from the experiment. These 3 matrices, by the way, this is the Majorana matrix. I will not talk about that too much because it doesn't affect the oscillations at all. Has to do with where the information comes from. This is mostly from atmospheric experimental information, and this is more from solar experiment neutrino information, while the middle one comes particularly from reactor neutrino experiments or accelerated neutrino experiments, which came a bit later in the game after the oscillations were established. And to start with that, so as I said, it's important to know this angle 1-3, if it is non-zero and at least also substantial. And the contributors to these measurements over the last, 10 years or so have been Daya Bay in China, Reno in South Korea, and Double Chose, which are experiments which are a few kilometers away. Well, they usually have near detectors close to the reactors, and there are several reactors here, as you see, which are going to contribute to the central point here, with some near detectors and some detectors which are far detectors in that language, about a few kilometers away from that. And you look at the disappearance, basically, of the the electron antineutrinos, which are the ones which you produce in nuclear reactors. And that's the result at the moment. If you look in the PDG, for that angle, you see that angle it's not big, not as big as the other angles which we measure in the 2, 3, or 2 to 1 sector, but it is substantial. Again, something like 8 to 10 degrees or so, which allows to have these terms in this PLNS matrix large enough so that we could extract the CP violating phase from that, which we measure. So that was good news. And the fact that we saw this coming since years has very much stimulated the accelerator program, going for long baseline experiments, which we believe now, thanks to the fact that this angle is large, that you can extract the information on this CP violating phase. That's a summary plot from a paper in Nature from the double choice experiment, giving sort of the summary of things. And what you do see there is the most precise measurement was already in 2018 and still is. The experiment is now being terminated by a bay of this value here for the sine squared to theta angle. So up to accelerator-based experiments. If you're new to this, this is just a cartoon how you make a neutrino beam at an accelerator. You hit a target with an intense and energetic proton beam. Can be 50 GeV, can be 120 GeV, is what we plan for doing, for example. In that target, you produce pions and kaons. You focus them as long as you have them around and they are charged. You can do that. And then you send them in a decay pipe or decay tunnel. They decay in pions, almost 100%, into muons plus neutrino. And the muon you stop, or whatever it is that came out of the decay with the charge. You stop here, the neutrinos goes on, they're somehow focused because of this here, that's your beam. This you send from either, for example, J-Park in Japan, to a near detector to monitor the purity of, say, the muons neutrinos you have, because there will be some background of decays going into an electron neutrino here as well. And then that you have to, you know then, what is going this direction. And on the way, your particles will oscillate, and what you will see here is different than what you would expect there. This is the oscillation part. I will show you dramatically how much it can change in a moment. Similarly, and running at this time, so this experiment is running now, and since years, and it has been producing results, and it's still going to probably double its statistics or so over the next few years. In the neutrino physics, we still work with few events, few hundred events typically, where all the information is coming out for this kind of experiment. And there is the American counterpart going from Fermilab with a beam sent 800 kilometers to a detector on surface there to be seen. Some more details are given here. I don't need to go to that. And this shows such a spectrum. This shows the disappearance. The important spectrum is the one in the bottom here. It shows the disappearance of neoneutrinos as function of the energy that the neutrinos have. And what you see is that, well, it's never really one. There is always some part disappearing because your bin widths are large enough to have always some effect. But at some parts of the energy, you have almost 100% of your neutrinos, muon neutrinos that have disappeared. That's calibrated on what you measure in the near detector. So this, from this kind of information, you get the muon or anti-muon disappearance effect. Because that's another thing for an accelerator, which is easy to do, is that you can select, for example, the pi pluses or the pi minuses with this focusing part. And depending on that, you get a neutrino or an anti-neutrino beam. So you can actually switch from one to the other. You don't do that too often. Typically, you run a few years or a year or so, and then the next year you go for the anti-neutrinos, so the neutrino beam. But that's what you need for something I will show just in a moment. Just for the record, this is the latest plot as I'm aware of it for sine 2 theta measurements combined from these either atmospheric neutrino experiments using that like Ice Cube and Super K, and the accelerator ones, Nova and T2K. And they each have their contour in the mass differences with the angle they measure, and you see they are consistent. But why do we need this neutrino and antineutrino beam? Well, that is the way to measure the CP violating phase. What that phase says in that matrix is that neutrinos and antineutrinos are going to oscillate differently if that phase is not zero. That phase could be plus 90, could be minus 90, which would be maximum sort of difference in the oscillation you have between neutrinos and antineutrinos, or any value in between. But 0 or 180 means no difference between these neutrinos, then this phase is 0. So that was a measurement released, I think, end of 2019, published really in 2020 from the T2K experiment, and this shows still the statistical level. On many years of accumulated data, I think it's like 5 years or so, they observed in a muon neutrino beam 90 events which were clear electron muon induced. So they have, you see them coming up as a chameleon with as an electron neutrino. And in the antineutrino beam, which is not as intense as the neutrino one, they saw like 19 coming up. What do they expect? If the phase would be 0, then so no difference between neutrino and antineutrinos, they would expect 70 electron neutrinos in the event in the file or in the data samples, and about 20 anti-electron neutrinos. So the intensity, as I said, for these beams is different, and also the efficiency for picking them out is different. What they found was 90-15. And if there would be like maximum CP violation in one direction, they would expect that 80-17 here. So this goes up with respect to that, this goes down, or the reverse, this goes down, this goes up. So it's still low statistics numbers. You see the distributions with the CP0 curve, the black one. The red one is the minus 90 degree curve, and the plus 90 degree curve is the blue one. And overall, what they got is that they could, with these data, at the moment, disfavor this region, if this is the whole phase space for the angles, let's say, no CP violation here, no there, maximum in one direction or maximum in the other. And that region is disfavored at 3 sigma. And the most likely value they get from these data, with large uncertainty, of course, points close to the maximum violation what they have here. So that made it to Nature, and the Nature called it a mirror cleft, and the Agatha Christie fans will appreciate that, probably know what it means. But the story is not finished there yet, because you see the statistical significance of the whole story is still something that certainly will need the additional data and the other experiment. This is T2K. For Nova, they have been starting a little later with getting the antineutrinos beams, so they were a little behind on that, but now they're catching up. And as you have it always with good neighbors, they don't necessarily agree. And also here you see that, for example, the Nova experiment gives much less strength to the CP violating phase as it comes out than the T2K one, and there's some level of disagreement in some areas for that. So the jury is actually still out what it's going to be. I think the world was quite excited when they saw what T2K saw, but maybe we have to temper it a bit, see what comes out. This is the last combination plot I saw. And what you see here, this is the likely curve of 68% of T2K and the 95% curve you have here. And this is the same, the 68% curve of Nova, which isn't quite as precise yet right now with statistics-wise, and the 95% curve. So here, they seem to be like almost telling the opposite. And that is for the normal mass hierarchy, which means the mass hierarchy where the very heaviest neutrino, or the neutrino number 3 as the highest mass. This is for the inverted one, when the neutrino number 3, the mass state, has the lowest mass. We don't know that from the experiment so far. Here they agree better, and they would agree on some maximal CP violation if these were the conditions of the data, but here's a bit more fuzzy. So we'll see. Data is being collected as we speak with upgrade detectors and in more intense beams, and we'll see what comes out. That's the dry list of all the angles and mass differences as we have measured them so far. The thing to see is that for 1, 2 and 2, 3, the angles are close to 45 degrees within aerofoils. 33 here, 49. This is called maximal mixing, which you have. It's about 10 degrees, maybe a bit low for theta 1, 3, but it's sufficient to hunt for the CP violating phase, which is not quite well known yet. Now, these are numbers. The pictures are better. Well, I will go over this. Pictures are better. These 1, 2, 3 mass states, how are they composed in either electron, muon, or tau flavor? Well, the one state is mostly electron-like, I would say, with 1/4 of a mix or equal mix of muons and taus. The nu2 state is as democratic as can be, 1/3 of each, essentially. And the 3 state doesn't like electrons at all, very small part in there, mostly it's neutrino and tau flavor state. That is how it looks like. This is what these numbers tell us in the picture. Compare that with the quark worlds. This is the CTM matrix. That's mostly a diagonal type of matrix with some off-diagonal parts, sometimes small bits. This is like how the between the flavor states and the mass states, the neutrino matrix looks like. It's not quite as diagonal as see here with quite substantial off-diagonal states. So very different. And of course, we don't know yet where that comes from. Okay, moving on from oscillations to maybe absolute masses. I think this is the champion at the moment for measuring absolute masses in a direct and least model-dependent way. They're just looking at beta decay, the endpoint in beta decay using tritium. And that's the Catherine experiment, which is operational since a couple of years in Cal. There's an interesting story with that apparatus and how it actually got to be where it has to be, but I'll leave that for questions, if any, or for drinks afterwards to tell that, who's interested in that. But in any way, this experiment is now measuring, well, it's working fantastically well. And the latest result they actually have is that the mass of the neutrino, which is actually not the, well, electron mass itself, but it's like a coherent sum or incoherent sum of the 1, 2, and 3 mass states as they are part of this making up these masses is less than 0.8 electron volts. So that's the first time actually broke down through the ground, seeing that the neutrinos are below 1 electron volt. That's a result of a couple of months back. Other experiments which have access to the mass, well, there are 2 more. You can have from cosmology, you can get information on the sum of the mass of the neutrinos. And that has, of course, quite a few assumptions in there to get to that number. These ones are also direct measurements, but assuming, or at least having in mind, that the neutrino could be its own antiparticle. And that is looking for experiments which go for 0 neutrino double beta decays. It happens that some nuclei, there are 12 of them or so that we know of, when they decay and they have a beta decay, that one single beta decay in that nucleus is energetically disfavorable. So it's not happening, it's suppressed. But the double beta decay, so two of the neutrons becoming a proton and sending out an electron and a neutrino, is energetically favorable, so that can happen. So these happen in these nuclei. What you get there is double beta decays at the same time within the nucleus. But of course, it happens with a reduced rate because it's double suppressed compared to a normal suppression of a beta decay. Now, the interesting ones are not simply the double beta decays, but those where you actually are not going to produce a neutrino in this, or two neutrinos in this double beta decay, because the neutrino will actually interact between the nucleons here and change its identity from a particle to an antiparticle and be absorbed here, such that there is no neutrino coming out of this process, but only electrons and the quarks that change here. So that is called a zero a double beta, the zero neutrino double beta decay. And that's something you must hunt in extreme conditions of background to control actually that you would have such a type of signal, which you can detect kinematically when you see the electrons coming out, that they are running away with all the energy and there is nothing left for the neutrino to happen there. And the Gaga experiment was a champion in that one. That has also finished the last years and produced end of last year its final observation, which unfortunately was zero events observed. So we still don't know if that process exists. A few events well above background would have helped, but it's not the case. But that pushes down under these conditions that process exists to mass limits in the order of 80 to 200 milli-electron volts. So, it could be very low, these masses which we have here. I will not say more about that. Let's talk a little bit about the future. This is the future with the sort of big experiments. There are many experiments or several experiments for trying to get improving the masses. Catherine will go to 0.2 electron volt in probably 3 to 4 years from now. And there are already new ideas to go beyond that, even beyond the 0.1 electron volt level, but they are still more in the planning.
Yeah, but do you have one?
The thing doesn't.
What? Can you connect to
No, I cannot. I am connected to this now.
yeah, this one won't connect.
I can try with the Wi-Fi,
Yeah.
and then I'm back where I was yesterday morning. So hold the press. Also, if you see a web page, my talk is on the agenda. You could take the PDF from there if you want.
I think you're already online.
Yeah,
On the
but this is the one which wasn't very successful before. I'm gonna remember this conference. Okay. It will be with delay, so I'm not sure how useful it's gonna be. Anyway, so the experiments are on this side. We have Dune. This is a very long baseline experiment with 1,300 kilometers baseline. Here we are going to have replaced the super K by an hyper K in for the T2K, which would be a T2HK then. There is a reactor neutrino experiment, a bit longish baseline here from Juno, which will look at neutrinos from the reactor and many other things as the other experiments. They will also look for supernovae, proton decays, and so forth. Spherics, which is in India. And on the pole, we will have the already existing ice cube experiment that, thanks, Zoom is ready. And they have already an experiment in ice here, and there is a proposal underway. It's in fact already 9 strings are deployed, not too far from here in the Mediterranean, more to the French side, where they use the water of the Mediterranean as a big detector and look for Cherenkov light for neons passing there coming from the neutrinos, basically from below the Earth, which come here. Let's do this test. Yeah, okay. So this is the thing that is going to cause a problem because I changed slide here, but it takes a while here. Now, okay. So for the long baseline experiments, that's T2K and T2HK and Dune. You will find on the slides the specifications here. And as long as it doesn't change, I can tell you a few of them. The energy of the beams is going to be different, and the distance is different. The 300 kilometers for one and 1,300 for the other. This is Dune underground. There are going to be 4 modules of this size here, 16 by 16 by 60 meter. So this is bigger than the Atlas experiment. And there will be just monolithic liquid argon time projection chambers. And first target for the neutrino interactions and precision instruments to measure the thing there. And that's where CERN comes in actually, because CERN is involved in prototyping this big detector with small detectors, which are about 4% size of what you saw before, but they are still 9 by 9 by 9 meters. And these are being done as a scale of 1 to 25 or so with the Dune detector module. And I said, so CERN had an intense neutrino program with their experiments, most on site, like CORS and NOMAD were the last ones they had. And as of 2000, due to a budget crisis in CERN, in fact, the neutrino program was stopped. They still delivered the beam for the Opera experiment, but the experiment they had nothing to do with directly. And then there was silence from the neutrinos during that time. It came back at the time, 2014, a few years after people realized that sine theta 1,3 was actually big enough to go for the CP violating phase. And every region said, we're going to do long baseline experiments again. Japan, extending the one they had, maybe with a possible hyper-K. For the US, it was Dune, or it was called still different at the end, the LBNE, but it became Dune. And CERN had its own experiment for seeing Laguna, but three of these big experiments, which are big and obviously really expensive, that looked to be too much luxury for the world that we could afford. And so CERN has actually said, we are not for a long baseline experiment. We have the LHC that's working after us, but we will participate in the program because, for example, for the liquid ion TPCs, we have the know-how how to help here, and that's how the neutrino platform came into action. That is also the neutrino group in 2016 came back into action. All right, so the next picture will just show you the PR picture for the neutrino, the so-called cryostat, which we have. Now we move it on my slide here while we wait for that picture to sorts of activity which we are at CERN on the neutrino platform. And I think there's no need to go into detail of that either, so I can move even further. And I hope you follow at some point, showing the whole of the neutrino platform and how you can actually connections again disappearing, folks. So they're trying for coffee here, I think. So I think just how that you can see. So if you don't do that, we're going to do this thing for water here. Fortunately, you can't see the virtual visit. So that's a movie of me showing actually people around for 1 hour, which we're not going to play now. The platform and biostats going into these cryostats, for example. I'm here. And going into biostats and seeing, well, you know, getting explained there in great detail by experts, not by me. I don't know if, well, as you can find it easily on the web once the web works again. There's something on the sterile neutrinos which I want to put your attention to. I'm not going to explain it. I'm going to leave Alexei on Friday, where there was actually an experiment, sterile neutrinos. That's the so-called neutrino 4 experiment in Russia. There is an enormous amount of criticism on it, whether they really see oscillations in these data. Or they generate, I'm just saying there was an instrument made at the reactor, another one in down, which just could not confirm this result. They're just not sensitive enough. I could tell you about the glacial resonance, which was seen in the ice cubing thing experiment. The glacial, yes. It's somebody's on my talk.
I think we have to wrap up.
Yeah, we have to wrap up. So I'm going to the conclusions, but you know. And who's in control? Okay. Just well, this was the neutrino platform. You can be in here. Go one slide down.
I cannot.
Okay. Yeah, I mean, it's getting a bit ridiculous. Am I in control? I'm no. And the other thing, just say by words, that's that's neutrino 4. And that's, you know, you'll see about Alex saying, this is what they measure as a possible sweet spot where you can where you have these neutrinos. Yeah, forget it. Okay. And this is the neutrinos for the LHC. And actually, I leave that. No, I don't. Fine. Conclusions. Oh.
You had 50 minutes. You've got enough.
Yeah, I had a lot of chaos also in this thing here, which was totally out of my, okay, as I said, I will remember this. So for the LHC, I want to say is you produce a lot of neutrinos at the LHC at very high energies, particularly in the directions where the beams are going, because the beam remnants, they fragment, they produce a block of pions and kaons, they decay, and it's like in a normal neutrino accelerator beam, by the decay, you produce your neutrinos. They are not focused in a particular way, but they come that way anyway. And what the idea is that around Atlas, if 400 meters away, and the accelerator will turn away with everything, and you can put detectors there. And in fact, neutral particles like neutrinos, they move on. They go through the rock, and they will come in these detectors. This is where 2 experiments are putting now detectors. For example, SND at LHE was approved 3-4 months ago. We're installing it now. And it will run beginning of 2022 when the beam gets back. And we will measure neutrinos at TeV energy scale. Never met it so far. And that's it. It was a rock ride. But you know, this is the end, and finally, for some reason, the summary is actually there. So you can look at it. That's all what I sort of touched on. And just giving you the prospects, the status of the PMNS type of measurements, and the prospects you can have. And ending, I say, you know, neutrinos actually, when they have mass, they create a crack in the standard model, because the standard model doesn't like them to have mass. The underlying reason is that they don't really interact with the Higgs field, because then they have a right-handed component. That's the chiral thing with the Higgs thing. It changes the isospin if you interact with it. So neutrinos don't do that. So they do something else to get their mass. And that is what people call beyond the standard mass, beyond the standard model. And but we're looking for more cracks, obviously. And neutrinos have given us a lot of surprises over the last, say, 20, 30 years, maybe earlier. And I'm quite sure we're going to be having many more surprises in there. That's also why I just don't do collider physics only, but also I'm interested in this thing. Okay, Paul.
Okay, thank you, Albert. So we can have some discussion. I think Neville has a question.
Yeah.
Neutrinos with V much less than C going through us. So how do you know that, and what's their origin? I mean,
So from what do I know? Which ones?
how do you know that? I mean, not you personally, but
That you radiate these neutrinos, or
how do we know that?
or from the amount of calcium-40 that is your body, which is 16 milligrams. And from that, you can calculate what the rate is.
No. All these neutrinos, V much less than C. I don't know what the origin of that.
Oh, the much less than C is coming from something I can't show now, but the spectrum, which I showed in this plot for the energy spectrum for the different neutrinos. There was this bump of the neutrinos coming from the cosmic ray background, coming from the Big Bang. And that has a spectrum that goes from something like a few micro electron volts up to what you have. This is the kinetic energy of these things. So given that you can assume the mass limits, which are the minimum ones you get from the oscillation experiments, assuming that everything is squeezed to zero and there is no offset, that gives you the idea of kind of, there is an error on that number. Yeah? It could be 10, could be 0.1 or something like that. No. One further. This one.
They must come from the weak interaction though.
It's just from this one, from the energy they have here. And if you have a certain mass, then you know what the speed is.
Because they must come from the weak interaction. They must be derived from.
No. What these are, they come from weak interactions, but it's like the photons in the CMB. They are cooled down over this 13.7 billions of years in energy, and that's the same thing.
Well, they're cooling, so but yeah, they're not interacting.
I mean, I'm not responsible for that theoretical curve. Maybe some theorists.
That is really strange. It's mind-boggling. Loads of right-handed neutrinos in there.
It's not something particularly disputed in the community, so I probably may not have the right words for it, but.
Okay, are there any other?
I didn't really understand the question, but the neutrino background is inferred from properties of the cosmic microwave background radiation and the fluctuations there that determines when the universe became radiation dominated. And that depends upon the number of neutrino species in the neutrino background. Does that help answer your question?
I think what he is worried about, how do we know the energy spectrum of these guys here? These were the ones created during the time of the Big Bang. They had probably energies as respectable as these had at that time. But due to the cooling of the expansion of the universe, that's like for CMB that these things cool down. So that's why they all shift like with the photons, they shift a low energy. Yeah.
Does that answer? I think so. It is surprising, yes, if it's true.
Well, that's why you can win something by actually going out and measure it.
Yes, of course.
If you have a good idea. That's right. There are some ideas, by the way, how to do it.
Since it's you, Neville, of course you can.
No, there was a weird plot you showed, probably a publicity plot. It was a circle with a 3 sigma excluded on one side and an allowed on the other.
T2K.
I didn't understand that at all.
Yeah. Okay. This I can explain again for Neville. So this has to do stop. One before.
Yeah.
Stop. One back. Yeah. Yeah, this one. So one part of this circle. Yeah. Listen. One part of this circle, right at plus 90 degree, you would expect this number of events. The other part of the circle, you would expect the other one. Because in one case, you will have more electroneutrinos being produced, and the other case, less electroneutrinos, but compensatingly more antineutrinos, and in the other, less antineutrinos. So it is, these two numbers tell you that you're in this situation, not in this situation. These two numbers, sorry, the magic ones. So, next slide. Therefore, this part is disfavored compared to this part. This is the 90 and the minus 90 part.
There's a 3p violating phase of 0, which has both. I mean, there's a point on that line that has both. You go suddenly from 3 sigma to allowed, right?
No, you go smoothly.
It's got to be a gradual.
You go smoothly. This is just where the boundary of 3 sigma is. Here is 2.9 sigma. Here is 2.7 sigma.
Okay.
And here is the preferred value.
I'm sorry, I misinterpreted it.
Okay, are there any other? Everyone wants to have coffee, I think. So
Yes,
let's
I have a question, please.
magnificent
Can
talk.
you comment? can you comment more on multi-messenger astronomy?
Sorry about the interruptions. That was out of everybody's control. And so we should come back in what time? In 20 minutes, which would be 6:25. 6:25.
First one was out of it was the first stop. But this one was out of our hands. It was just the last. It was the power company that did this to us. I'm sorry.
You did a great job. No, it was a good.
If you're more like an entertainer than and then prizes manager than speaker.
Well, I would make a comment like that. That is